Hello everybody, welcome to chapter 7.3 part 2, Pythagorean Triples. Pythagorean triples are sets of non-zero whole numbers, say a, b, and c, such that a squared plus b squared equals c squared. These are called Pythagorean triples. And a few Pythagorean triples are 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25, where the first two numbers, for example, 3, 4 are the legs, and 5 is the hypotenuse. 5, 12 are the legs, and 13 is the hypotenuse. 8 and 15 are the legs, 17 is the hypotenuse, and 7 and 24 are legs, and 25 is the hypotenuse. There are many more Pythagorean triples besides the ones listed, but they must be in the proper combination where a squared plus b squared is equal to c squared. So let's look at a few. We're going to look at example number 7. Find the missing length, like we did before, using the Pythagorean theorem, and then we're going to see if indeed this is a Pythagorean triple. So let's work on this. Of course, we start off with the Pythagorean theorem and we decide which one is going to be A, which one is going to be B, and we plug in the two legs. So we're substituting in, let's say we make 14A and 48B, and we want to now solve for C. So there we have this. Now we want to take the square root of that, and we find that C is equal to 50. Well, 50 is a whole number. So in this case, the side lengths are non-zero whole numbers. So this is 14 is a non-zero whole number, 48 is a non-zero whole number, 50 is a non-zero whole number, and as we just showed, they obey the Pythagorean theorem. In example number 8, we're asked to find the missing side length and tell if the side length form a Pythagorean triple and explain. So we have the Pythagorean theorem, a squared plus b squared is equal to c squared. And we have this triangle where we have one of the legs is 4, one of the legs we don't know, and the hypotenuse is 12. Well, usually A and B represent the legs, so we'll substitute in 4 for one of them. We'll leave B alone since we don't know what this leg is, and we know that C is 12 because that's the hypotenuse. Then we multiply and subtract 16 from both sides because 4 squared is 16. And we find the positive square roots, meaning we look for the hidden perfect square, and we find out that that's 64, and 64 times 2 is 128, and the square root of 64 is 8. So that's how we get the 8 here, because we took the perfect square, 64, and pulled it out, and we were left with 8 square root of 2, since the square root of 2 is not a perfect square. Unfortunately, the side lengths do not form a Pythagorean triple because 8 square root of 2 is not a whole number. In example number 9, here we're going to find the missing hypotenuse, or C. So we're going to go about it in our usual way. We're going to plug in the legs. Here's a leg, and solve for c squared. And we're going to take the square of those. So this is 64, and this is 100. So 100 plus 64 gives me 164, and then I take the square root of both sides and simplify. It turns out I can't simplify any further. So just like in number 8, we have a square root here. This is not a whole number, so therefore this cannot be a Pythagorean triple. In example number 10, here we're missing a leg. So we want to see again if it's a Pythagorean triple when we solve for what the length of this leg is. So we go about it in our usual way. So let's say we make 24 equal A and this one B. So that's what we're going to solve for. And we multiply and subtract just like we would a regular algebraic situation. And then we find that b is equal to 10. So if this is 10, this is 24, and this is 26, that means that all three of these are whole numbers, and just like we showed, they obey the Pythagorean theorem, so then that means that this is indeed a Pythagorean triple. In example number 11, we're going to find the missing side and round to the nearest tenth, tell if the side lengths form a Pythagorean triple. Well, we can say right off the bat that there is no way that that is a Pythagorean triple, because this is a decimal, so therefore that is definitely not a Pythagorean triple. And the fact that we're asked to round to the nearest tenth, that tells us we do not have a Pythagorean triple going on here. So no, the length of 2.4 is not a whole number, and therefore this cannot form a Pythagorean triple, even if we solve it accordingly. In number 12, we're going to find the missing side, and we're going to see if it's a Pythagorean triple. We have nothing telling us that it can't be, so let's try. So we use the Pythagorean theorem the same way as we've done in the past. And we'll take one of them, we'll substitute 30 for A and 16 for B. And then we'll multiply and solve accordingly. And we find that when we take the square root of 1,156, we get 34. And 34 is a nice whole number. So therefore, this is a Pythagorean triple because this is a whole number. The hypotenuse here is a whole number, and as we just showed, it obeys the Pythagorean theorem. And similarly, for example number 13, we're going to find again the missing length and see if we get a nice whole number. If we get a whole number, it will be a Pythagorean triple. If it's not a whole number, it will just be a length. So here we go through it. 12 squared plus 5 squared is equal to 144 plus 25. And I took the square root of that for C. So that means it's the square root of 169 is equal to 13. So what I did is I have 12 squared. That means 144 plus 5 squared is 25. And then I added these two up. I got 169. It turns out that 169 is a perfect square. So this is indeed a Pythagorean triple, 5, 12, and 13. And as we just showed, it satisfies the Pythagorean theorem, and these are all whole numbers. Thank you very much. I hope that you enjoyed this video. Be well and take care, and goodbye for now.